welcome everyone. So welcome to the fourth lecture, where we are going to be dealing with the last bits of what we call a power diode. So today let's look at a few things. One, those are the conduction modes of a power diode. All right. So conduction modes are nothing more than a summary of how the diode will behave in different biasing configurations. So we have a couple of those. We have what we call the forward conduction mode. So this is where the diode is forward biased. That means we apply a positive voltage or a voltage, let me call it VA, whereby it's greater than the voltage at point B, VB. So in this case, let's say we take that side to ground, or it continues all the way to a load, then to ground. All right. So let's say the current flowing through that diode is IF in the forward bias mode. So I'm talking about a real world, a practical power diode in this setup. So this is what we have. Let's say if it conducts like an ideal switch, let's first look at something, because the diode in this case is just going to act as a switch. So let's look at an ideal switch. Right? So brief detour. So an ideal switch, when it is open circuited, in other words, amps flowing are equal to 0. No amps flowing, right? So the resistance in this case is infinity ohms. So we expect no power losses across that ideal switch. So when it closes, let me denote it like that. When that switch closes, right? Let's say it closes, a certain current I will flow, and it will no longer be 0 amps. A certain current will be flowing in the order of amps or microamps or milliamps. So we get the point. So the resistance across that switch, an ideal one, is 0 ohms. 0 ohms. So the power loss across that switch while in conduction, or conduction losses across that switch, are equal to 0 watts. Because remember that power is given by I squared R. The R part is 0. So we expect no power losses across an ideal switch. For ideal scenarios, that's it. And the voltage drop across it is 0. VPD is 0 volts as well. So a practical diode, because this is a practical diode. Okay, under forward conduction mode, current IF, forward in the forward direction mode, flows, and a voltage drop, VPD, across it is detected. So the moment we have a voltage drop across it, and if we multiply it with the IF, the forward conduction current, we end up with the power loss across the diode, PLD. I'm denoting it with PLD. So we have power losses. So in forward conduction mode, we have such losses. That's nice. So that is one mode. The other one is reverse. Reverse blocking mode. We still call it blocking mode because no noticeable practical current flows in reverse. And this is when the diode is reverse. This is when the diode is reverse biased. That means that's the negative. The voltage drop across it is now negative. So we have IR, a reverse flow current in the order of microamps. In the order of microamps. Still, here we'll have power loss like we had power losses with the forward conduction mode. In the reverse blocking mode, we'll call it blocking mode, but still a little current flows through, makes its way through. Here the power losses are minimal. Let's just denote it like this. Power losses are negligible. That's the right word. Negligible. Very negligible. We can neglect the power losses because most of the current, 99.9% of the current is blocked. Here the word 99% or a bigger percentage of the current in the reverse direction being blocked. It does not mean it does not conduct in the reverse all the way. We are going to look at that. So the other mode is reverse breakdown mode. Here still the diode is reverse biased. Guys, let me switch over to this side. With the reverse breakdown mode, let me just abbreviate it as so. So with the reverse breakdown mode, the diode is still reverse biased in the order of microamps, like we've said, in the order of microamps. But still, hold on, still it's not in the order of microamps. Actually, this is now in the order of couple of amps. It's in the order of couple of amps, right? Because now this is where now the reverse, this is where the reverse supply voltage or voltage drop across it in the reverse direction exceeds VBR, the breakdown voltage of that power diode, where it breaks down, whereby it no longer blocks current, like it's actually a direct short. Here the diode is equivalent to a direct short. So it conducts the current all the way to its maximum in both directions. This is where now the diode is deemed damaged and broken. So guys, this is it for the conduction modes of a power diode. So we have the forward conduction mode, that's 1. The reverse blocking mode, that's 2. And the reverse breakdown mode, that's 3. We are not yet done with the power diode. So let's head over to the next sub-chapter that closes power diodes. Losses in a power diode. All right. So whenever we are delivering power, think of it this way. Let me build for you an analogy. Let's say you're sending money over through mobile money over to someone, and you send 10,000 shillings. For some reason, what gets received on the other side, instead of it being 10,000 shillings, you receive 8,000 shillings. So, and there happens to be another way of sending money, whereby if you send 10,000 shillings, you can get, let's say, 9,500 shillings. Automatically, you're going to go with the 9,500 shillings method, because it delivers almost all of the contents of the package, in this case the money, to the receiving side. The same story goes for power manipulation, delivery, and other technicalities. The same goes for delivering power. So let's say we have 7 watts of power to be delivered from the source to the destination. All right. So if we deliver 50 watts, and what gets used by the load, let's say it's for lighting, heating, driving air around, those are motors. And when we calculate what the load has used is not equal to 50 watts, but it's less than 50 watts, that means we've lost some of the power along the transmission system, right from source through the conductors, the switches, and down to the load. That's very important. So power diodes are no exception. So power diodes in real life inhibit or manifest signs of losses. So we have majorly 2 types of losses in a power diode. The very first one, that is the very first loss we have is the conduction loss. This happens when the diode is conducting in forward conduction mode. So let's say the conduction forward current is IF and the voltage drop is across the diode, not the load, across the diode is VPD. The power loss conduction, P conduct, is approximately equal to IF times VPD. That's interesting. So, like we talked about this in the previous subsection, that a real power diode constitutes of power losses during conduction. The other loss is switching. Switching loss. So a power diode, we saw how it operates. We saw how a power diode operates. It takes time for its PN junctions to operate, for the charge carriers to drift, create the voltage barrier, the potential barrier, the depletion layer. That takes time. And depending on the switching frequency, in which the diode is being placed, the switching frequency of the circuit in which the diode is situated, we will have the diode, very important note, sometimes the diode is going to conduct almost free in the reverse bias configuration. Before it blocks current in the reverse bias mode. Very, very, very important. All right, now let's say we have a block that represents the power losses in a power diode, right? So a huge portion of that, a huge portion of that is due to what we call conduction losses. And this is typically in the forward bias conduction mode. So the remaining part is from what we call switching losses, right? So it's what is from what we call switching losses, the remaining portion. So a huge portion of how much power a power diode can dissipate or power losses in power diodes are mostly contributed towards by conduction losses. So conduction losses can be approximated as follows. So let's say we have a typical power diode, that's the symbol. Let's say it's forward biased and it has a forward current, conduction current IF, and a voltage drop VD across it. So the average power loss can be approximated as follows. We have VD multiplied by IF. That would be the conduction losses. So this is what we would call the conduction loss in that power diode. So the other kind of loss, that is, this is the conduction loss, this is so the other one is switching loss. So this is a kind of loss that happens as the diode is transitioning from forward conduction mode to reverse blocking mode. That transition takes time. It's not instantaneous. So like the way we're used to demonstrating it with our voltage time graphs that describe how, let's say, a power diode rectifies a 50 Hz sine wave, right? Sine wave, let's say in sine wave rectifiers, right? So we will look at wave shaping and rectifiers. So we are used to representing that voltage in volts like so, allowing voltage at certain time and cutting it off completely at another time. So yes, this works for small switching frequencies. This is perfect. This is correct, right? This is time in seconds, right? So this is correct. But let's say, like we are going to see in this course unit, we're going to have what we call switching regulators. We're going to have what we call switching regulators. So switching regulators typically operate at around 40 to a few hundreds, could be 200 or even 500 kilohertz of switching frequency. So these diodes need to handle high frequencies, right? So this is when the diode, if not selected right, will dissipate the most amount of power. That's when it will create the most amount of power losses. Very, very interesting. So in such scenarios, we will have a moment whereby the diode is conducting even in reverse before it fully blocks the current in reverse bias direction. So that phenomena is something we call the reverse recovery of a diode. So the time it takes for it to switch from forward conduction mode to full block reverse blocking mode is what we call the reverse recovery time. So this time around, let's look at what the current is doing as we switch with respect to time, the forward conduction current, right? Or let's look at the diode in both aspects, in forward and reverse. So if have the current I in amps, right? So let's say this is our forward conduction current, the maximum load current we're having at the moment. Let me call it IF, right? So let's say it goes to 0. So from the time that current goes to 0 and back to 0 again, now this time around in full reverse mode, this could be seconds or this could be in microseconds. Because typically it's in microseconds. This time frame is in microseconds. So what happens is that the diode is going to conduct even in reverse, right? Then asymptotically approach 0 as time goes on, then gets back to 0. So let's say in reverse, the maximum allowable current is IRM, right? So the time it takes from, let me call it T1, from the time it takes the forward conduction current being 0 amps to a quarter the maximum reverse conduction current IRM, which is around 25% of IRM, that time, the whole of this is what we call the reverse recovery time, TRR. So TRR is equal to, is given by T1 plus T2. T1 plus T2. Very important. So it takes time for the charge carriers to rearrange themselves in a way to oppose the reverse applied voltage to the diode. That time counts because this is going to happen typically hundreds of thousands of times per second. So what does this tell us? So there is a ratio, right? There is a ratio that compares the time it takes from the maximum then going back to 0, maximum reverse current, that is T2 over T1. That ratio is called the softness factor S. S stands for softness factor. It ranges between 0 to 1. It's a ratio. It has no units, right? Because we are dividing time by time. So this will determine which kind of power diode we have. We get it? So this is where we have the general purpose power diode. I urge you to research the voltage, current, and the reverse recovery time ratings of such a power diode. The other one is, so let me write the other one right here. The other type, this is the first, this is the second type, this is the ultra fast. Ultra ultra fast power diode, ultra fast power diode. So the third one is the Schottky diode. They all have three of them. They have voltage, current, and time, reverse recovery time ratings. I urge you to research on that. So I will not provide that information, students. So you will take time and absorb that information from your best sources. So that is how we conclude. That's how we get to conclude this chapter of a power diode. So in the consequent lectures, we are going to be looking at fully controlled switches. Diodes are among the uncontrolled switches because their turn-on conditions have nothing to do with an external control signal. Just the supply voltage just has to exceed the forward threshold voltage, and the diode is all the way into full conduction mode. We can't have anything in between. It is either off or completely on. So we will look at such things. So the remaining switching power semiconductor devices like transistors and what, we will cover them as we unveil other sections of the course unit. Otherwise, I can't keep covering them individually. That will be a different course unit. So I will keep on covering them as we cover other parts of the course unit like switching regulators. So guys, that's it. In the next lecture, let's look at tools and materials we use in power electronics, because we intend to cover this course unit with practice and theory. So let's have a quick dive into power electronics materials and tools. Thank you for being great listeners and learners. See you next time.